So in this video we're going to learn how to integrate and differentiate the natural logarithmic function, extending what we already learned in the previous section. So let's start with the function y equals e to the x, and let's suppose that we want to find its inverse. So we're going to switch the variables. So we get x equals e to the y, and then we're going to solve for y. And when we solve for y, what we need to do is take the ln of both sides. So we get ln of x So we get ln of x is ln of e to the y, and in simplifying, that gives us what? Ln of x, and ln of e to the y, well, that turns out to be, let's go to the next blackboard and see what it turns out to be. So here is the graph of y equals e to the x. Here is the graph of y equals ln x. And this right here is y equals x, and it's clear, isn't it, that these two functions, y equals e to the x and y equals ln of x, are reflections of each other about y equals x, and so the conclusion of that is that y equals e to the x and y equals ln x are inverses of each other. When functions are inverses of each other, they obey this property, that if you take the composition of a function and its inverse, or an inverse and a function, you get back to x. That looks perhaps a little funny, but if we look at an easy example for a function that we already work with, we know that x cubed and the cube root of x are inverses of each other, right? So here's the function, and the cube root is the inverse, and when we take the comp of those, we get back to x. And so how does that help us? If we go back to where we were in our derivation, we're taking the composition of ln and e, and they are inverses of each other. That gives us the x, or the inside part. The inside part in this case is not x, it's y. And so we get ln x equals y. So we just verified in this derivation that ln y and or ln x and e to the x are inverses, but we had to appeal to the graph to do this step right here. So how does that help us in calculus? Let's see on the next blackboard. So we're going to use what we have learned so far to find the derivative of e to the x. And so let's start by taking the logarithm of both sides of this. And our left side is just ln y. On our right side, we're using again the fact that ln and e are inverses of each other, so we get just x out. Now we're going to differentiate both sides. So we're going to take the derivative with respect to x of both sides. Easy on the right side, derivative of x is just 1. On the left side, however, that is a composite function, so its derivative is the reciprocal of y times the derivative of y. And when we take this and solve it for y prime, we get y prime equals y, since we're just multiplying both sides by y to do that. And so y prime equals y, but what is y? Y is e to the x, and so what we've just derived is that the derivative of e to the x is the function itself. We can extend that property and say, well, what if we have a function y equals e to the u of x? What would its derivative be? That would be e to the u of x times the derivative of the power u prime of x. And so if we have a function, as an example 1, e to the x squared plus 7x minus 5, and we want to differentiate that, we get the function back, e to the x squared plus 7x minus 5, but it's multiplied by the derivative of that function. And we want to extend this formula further to the case where if we have a base that is not e, what is the derivative? And let's note that if we have a to the u of x, that is the same thing as e to the ln of a to the u of x. So let's make sure we're clear on why that is. That's because e and ln are inverses of each other, so that gives us back to what we started with. And why is that good? Because if we use logarithm properties, one of the logarithm properties that we have is that if we have ln of a function raised to a power r, we can bring that power down in front. And so if we continue with this derivation, we're going to bring this power right here down in front, so we get e to the u of x times ln of a is our y, or written a little bit differently, y equals e to the u of x, e to the ln a, which is a constant, times u of x. So we've taken our original function, which was y equals a to the u of x, and we've rewritten it with a base of e. So now we can differentiate it because we just have e to a power, so the derivative of it is going to be what y prime is the function itself, e to the ln a times u of x, times the derivative of that power. And what is the derivative of that power? By the product rule, if we call this f and this s, it's fs prime, which is ln a u prime of x, but then f prime is 0, so that's all we need. And now if we clean this up, we get y prime equals, all of this is just a to the u of x, the function we started with. Here's u prime of x, and the only thing that we've added in that's different than the formula we had before was an ln a. So it's just like differentiating e to the u of x, right? Remember this formula right here, and the only difference between that and our formula, our new formula, is that we have this ln of a, right? It's still the function itself, the derivative of the power, but now we have this ln of the base. And just one more thing, if we go back here, ln of the base here would be ln of e, and ln of e is 1. So let's apply this formula in a like example 2 on page 146. So let's look at this again, and let's label these three terms: the adjusting factor. The three factors of this are the adjusting factor, the ln(a), the derivative of the power u prime of x, so the adjusting factor ln of a, the derivative of the power u prime of x, and the function itself, a to the u of x. So the adjusting factor in this case is ln of the base 2. The derivative of the power is 3x squared plus 3. And then the function itself, 2x cubed plus 3x minus 5. And now let's do an integral example, example 4 on page 148. So we notice that this x is the derivative of the power, so let's make u equal the power, so u is x squared plus 16, du dx is 2x, and du over 2 is x dx. So x dx becomes du over 2, and then instead of 4 to the x squared plus 6, it becomes 4 to the u. When we integrate this, if we had e to the u, it would be just e to the u. Here it is in part just 4 to the u. The adjusting factor, as in the derivative, is going to be ln of the base, but it's not times ln of the base, it's multiplied by ln of the base, and so there is our answer, but we would convert it back to, convert the u back to x and get this. So when we're differentiating a base that's other than e, we have to multiply by ln of that base. When we're integrating a base other than e, we divide by ln of that base.